Okay. Safi. No, Safi Baraka. Now I'm just gonna continue then with the agenda that I was told to teach. So for the next hour, I think we're gonna be brief actually. I don't think I will use the 1 hour and a half. So which means that I hopefully have more time to interact with you. So I hope you ask questions a lot so that we can reach to 3:30. But then I will show you an example of simulation. So for now, I will just prepare the grounds for simulation. So far you've got a notion of the basics of solar energy, the basics for the main technologies, trough tower. You also have an idea now of what the prices are or costs are for CSP as a system perspective. And you also understand better the technologies for thermal energy storage, how you can classify them, and the ones that are commercially deployed, which is just the tanks mainly. And the idea from this session in the afternoon, like I said, I don't think I'll need the whole time, but it's mainly focusing on how do we model and what do we look when we model, how do we design systems, okay? So, I will use my stuff here. I forgot where I have it. Okay, so when looking into modeling, when looking into designing or operating a system, you know one thing now, which is that the system, or the demands from what the system is supposed to do, technically, can differ. I mean, they will be different depending on the role that the plant is to have in a specific market, because it needs to operate at 9 p.m., or because we need 100 megawatt or not 20 megawatt, or so those are demands from what we call the off-taker, the one that wants the electricity, right? Which could be a customer, a single company, or it could be the state-owned company, like the ONA or whatever. Truth is, though, that there's more than that. I mean, another thing I want you to keep in mind from this, before we move into the actual design and operation, is that there are many actors involved in the project development of a CSP plant. And actually, not only in the CSP plant, this applies for most of the renewable projects. It's like, what is the actual, who are the people involved? And because the reason why I tell you this is because depending on where you are, you have different purposes for designing, different purposes for operating. I mean, so look at it, if you could put the head of using the same map, but then you say, let's say the case of Morocco. The governmental agency here is Masen. So Masen will be like my green thing here, right? So Masen has a role when it comes to promoting the projects, because Masen has to design the tender in which basically all the requirements for the plant are set up. Masen is saying, okay, I invite all of you power plant developers, companies, that to build up CSP plants, so already they say CSP, with a capacity from 100 to 150 megawatt, with a storage of at least 6 hours, and in this land area. So Masen takes care of that. And it takes time for Masen to decide where is this going to happen. It takes work. And for instance, in Warsasat, we had 3 different tenders. So for NUR 1, NUR 2, NUR 3, well, and then NUR 4 for PV and so on. And now Masen is having a tender open for NUR Midelt, which is the next complex. That's one major actor. And Masen has objectives that are not necessarily the same as the other people here. I mean, Masen's objective could be to create jobs, to guarantee reliable energy after 9 p.m., whatever. The one that builds the plant, let's say the developer, the only objective, and this is, if you put back into perspective, this is a business. So for everyone but Masen, everyone here wants to make money. And of course, they want to design the plant in the way that they can make more money. So that's something you need to keep in mind. I mean, this is a business. So probably Masen profits in different ways than just money. Although Masen is also making money. I mean, Masen, if you look at the way the projects are built here, Masen is owning the plants after year 25. So they will make money. I mean, they're getting a new project. But, I mean, for all of the rest, a development company for any project, I mean, CSP, PV, whatever, makes money by building projects and then making sure that selling it to operators, selling electricity, etc. That's the way they make money. A technology owner is, for instance, the company that builds the receiver, that builds the heliostats. The way they make money is selling heliostats. So if you ask them how to design a plant, alone, they will only want to design a plant that you need 40,000 millions of heliostats, because then they can sell 40,000 millions of heliostats, right? I mean, that's their business. So, I mean, this is the reason why I bring this is because this is a complex, environment. You have different people with different purposes. If we are to buy, if they want to sell as many heliostats as possible, we know that the cost of the system will increase, which makes your project proposal less competitive when competing with the rest. So the developer that wants to get the project needs to make sure that this doesn't happen. The same happens with the engineering. Engineering companies, or the ones construction here should be contractors actually. Contractors make money by a development company tells the contractors, here you go, we won a project in which we said that we were going to build a project for $600 million US. So we have finance for $600 million. That's why we're supposed to invest in equipment, in construction, in all of this, right? Then the engineering companies basically get this money, and this money should cover for all the equipment and their margin. So how do they make money? By increasing the margin, meaning by making sure that if the development company has a pool of 600 million, and the engineering company knows this, then, or this is the budget allowed, then basically they will try to get the cheapest components, which are not necessarily the most efficient ones, such that the plant complies with the minimum requirements and they can increase the margin. So from the cheapest to the 600 million, right? That's their business. But then again, it's the role of the developer to check that they don't just go for the cheapest Chinese components, because then maybe from a system perspective, the plant ends up being something that is not what they were supposed to bid for. But again, the core point here is that, so they profit by creating a project, the government, Masen, and by owning it later. They profit by getting the project and selling electricity to Masen for a number of years. Then they profit by selling the components to the engineering contractor team, which is actually contracted by the developer to build the project. And they profit by making a larger margin between what the developer pays them and what they pay the tech owner. So like, again, if you ask them to design the plan alone, and no one checks them, they will try to comply with some minimum requirements in the cheapest way possible. So probably for them, because they basically give away the plant in the operation stage. So once it's built, and the day it's built, or for the first year, it works as it should, they just give it away to the operator. This is it, we built it, right? But how do you know if they go for all the cheap stuff, the plant will work well the first year, but what about the second, the third, and the plant should last 30 years. So it's a whole, it's not only them, it's not only them, it's not only them. There's an ecosystem here. And each one will try to design the plan in the best way for them, the way they can profit the most. If you look into different steps then, after I've said that, you will then first have usually these steps repeating every competitive bid tender, or basically a tender in which you are required to compete and one project will get it, right? That's what's happening, the way power plants are promoted in Morocco. And these kind of steps will repeat in all of them. First, the tender is designed and launched by the government here in Masen. A development company, usually called SPV, or basically a project company, which is basically a consortium saying a developer together with a tech owner with an engineering firm, they say, we are going to bid. This is led by them, by the development company, which makes money on building projects. They prepare a proposal, they submit the proposal, the government evaluates the proposal. After evaluation, if one proposal wins the project, let's say, and then a whole phase of, to do this, I need to get the financing. And this is a very important step because at this stage, they're building a project with their own money. They prepare all the works and so on, engineering, pre-engineering, without having paid anything. But here, then, if they get a contract on the premise that they can build what they promise here, they need to go to banks, and together with some own money, There's usually a ratio here of 20-80 in CSP plans, meaning 20 comes from own money from the development company or equity holders, you say. And the 80% left comes from debt. So it could take up to a year or 2 years. Nowadays it's lower, it's reduced this time, but it could take up, even today, 6 months to a year to secure the other financing. Because if you're talking about a 600 million projects and only 20 you have, or 20%, you're talking about we need to go out to the banks telling them, look, we have a contract with Masen for 25 years. We come in with, I don't know, 120 million. We want a loan from you. And then one bank could say, oh, yes, we put 50 if they buy in. But 50 is not enough. So you need to go to another bank that puts another 50. You need to go to another bank that puts another 100. That process it could take a year. And each bank will put their own conditions, their own debt conditions, like this is my interest on the loan, this is my interest on the loan, etc. This is where other people come in play because the creditors are the ones that finance the plant at the end. 80% of the money comes from these people investing that not necessarily care about the technology as you do. They just see it as an investment, a long-term investment. In 20 years, I'll see my return on the money. That's how you build it. Again, if you ask them how to design a system, it's on their own interest that the system performs well for 20 years and so on, but they will have a different interest. They make money on the fact that the plan goes well, basically. And they don't necessarily have the know-how to know that, so they will contract other people in the ecosystem that I'm not showing here, which is people like me. So people in the financial institutions will go to people that are consultants and say, like, look, we're about to invest in this stuff. Does it actually work as it should work? Something like this. So there's a whole, I was asking the lunch, where do we work when we graduate from renewable energy? In any of them. So some people are working, developing projects, some are developing heat exchangers, some are in the construction part, some are in the government part, like Masen or stuff. Some are in the financial institutions. Some are, of course, in the operation phase, like on-site people working during the lifetime of the plant. Some work from if you look at in the steps after financing, once you say, yes, we have the 600 million, let's go ahead, construction begins. Construction is led by the engineering firm, the one that is constructing, right? Together with the developer and the tech owner, because they need to they usually launch tenders to get the supply of equipment. So they launch a tender for the tanks, they launch a tender for the heat exchanger, etc. So different companies that produce this equipment come here and win a tender with them. After the plant's being constructed and proven to work as expected, they hand out the plant to the owners. And the owners could decide to operate the plant themselves or to subcontract an operator, which is another entity here. The operator makes money by making sure that the margin, that what they get paid for operating with regards to the cost of operation is increased. So they have their own purpose. They have their own business. So you see and then the operation lifetime, which could be 25 years. So we're talking here, year 0, this could take a year. This could take actually another year or 6 months. This could take 6 months to a year. This usually takes 2 years. And then we're talking a 25-year operation lifetime of the plant. So all of this is needed for building a project. And here we have another entity that is important, which is the interaction with the grid. If the plant is to be connected to the grid, then of course, in case of Morocco, ONE has an important role to play here because at the end of the day, ONE owns the grid. So it tells you, it gives you the signal, yes, go ahead, go online, no, go online, and so on. So it's a natural interaction here. And ONE profits also in one way, which is not necessarily making money, but making sure that the electricity is there when they need to. And so there is a different profits here for everyone, and each one of them will design the system according to the way they can make profits the most. So I just wanted to have the background because depending on where you stand, you will design a system one way or another, or you will try to persuade the other one to tell him that this is the best system. Because in this way, if I work in a company that is selling receivers or stuff like this, I will always try to persuade, within reasonable margins, of course, my consortium that the largest receiver, the better. I don't know more reasons. And then It's up to the consortium to get it to decide, no, it doesn't actually make sense, for instance. Because I make money on selling receivers, so of course I want to sell a large one. See the point there? Okay. If we put it into time, this is what I just said, but this is the actual case of Morocco. So if you look at NUR 1, the whole beginning of NUR 1 started in March 2010 with what they call like a call for expression of interest. So this is a document, an official document that is released by the entity, government entity here, in this case Masen, which basically calls for expressions of interest. They say, we think there's going to be a power plant coming up. We want a power plant coming up based on CSP with these general characteristics. This document is made public and gets the attention of most of the known developers in the world or so on. And then they need to submit an application, which at this stage is very much only an interest, saying like, we, Aqua Power, we, whatever, have the minimum requirements for applying and we are interested. So like us, this is the very beginning. We're talking about March 2010. In July 2010, then there was a request for, I think this RFQ was basically a request for qualifications, which is like making sure that all the ones who said were interested met some conditions. I mean, of course, if a government is going to look into a company building a $600 million project, they need to make sure the company can comply to that. They have the background to that. They have a financial muscle to build that. They have built similar projects before, etc. They have the technology know-how, so they know the heat exchangers you're talking about. That happens here. So you say, okay, out of all the people who said it was interested, only 10 are actually qualified. And then, if you look at this, like after a year later, then they launched a request for proposals, which is a year later than after they said, we think we have an idea, who is interested, they saw that there is interest, then they called for a project proposal, saying like, okay, we need a CSP plant in Ouarzazate for this area, etc. This is the first time Masen did it, so they realized that their proposal, they got feedback immediately from the first developer companies, saying, you know, this is not fully right, you should look into this, and so on. So the request for proposal was modified 3 months later, like request for proposals too. So it's like they modified the conditions. And then a year later, so all this time, the companies prepare the project on their own budget. Saying like, okay, we need to prepare a project for NUR 1, and they made a bid, meaning there is a deadline. On that deadline, we submit all our documents showing that we have the financial possibilities to build it, that we meet all the technical requirements, etc. And then 6 months after that, Masen said, Aqua Power won the bid. So we're talking like, from here to here, 2.5 years passed, nothing has been built. Nothing has actually happened. For any user, like if you're in Ouarzazate, you don't have no clue that all of this happened. Now, after it has been awarded, until June 2013, nothing has ever happened. So you have a year where Aqua Power had to go outside and try to see who is going to put 500, whatever it would cost, 200 million in this with me. So all this year, it took Aqua Power to get financial closure, which means it's just a day where Aqua Power boss calls everyone and says, like, we're in. We finally got all the money we need. And you could imagine, I mean, when looking into the backgrounds of all of you, you don't need like many engineers to do this. This is just mainly finance. But like, so this is a whole. I was asking the lunch, like, so what's better, like materials engineer, chemical, like, you all need it. I mean, like, this is you need like, you have a chemical part of the process, you have a mechanical engineer part of the process, you have a financial part of the process. Once it reached financial closure in June 2013, it was not until 3 years later that this process took, like, the construction happened. And finally, in 2016, in February, it was a day where the king went there and said, you know, NUR 1 is officially inaugurated. But then if you look, it took, for this very first plant in Morocco, it took 6 years, which you, as a normal user, don't see. But this is the ecosystem. And again, in all of these steps, there are different actors, and all the actors have different purposes. They want to design in one way or the other. I like to say this slide because it's only like, I mean, if I don't teach this, then you only get the idea, you know, like this is the technology, this is it. But there's a business to this. This is like, if you're going to work, most likely you will not end up in academia like me. you're gonna go and find a job. So this is how the system works. Like this is the whole, and this is not only for CSP, it's also PV, wind power, so on. Then what happened in the second and third projects, NUR 2, NUR 3, which were a common tender, you see how Masen learned way faster. I mean, like, so the first expression of interest was launched in 2013, January, and in 2 years, we had already financial closure. So all of this experience gained from Masen was shown literally in the latest 2 projects. And the same could be seen in the cost reduction. I mean, like, now Masen was seen as Morocco as a more attractive country to invest. And you could see directly the first project was awarded here in 2012 for $189 per megawatt hour for a 25-year contract. And the second and third were like 140 and 150. So like already a reduction, considerably reduction, that in most of the cases, it's not because it got super cheap to build that compared to before. It's just the trust. Like, it actually works to build in Morocco. The plant's soon to be commissioned here. Masen has acted very well. The active financial, I mean, the banks now realize that it's actually business there, etc. So the ecosystem for these projects was already there. So of course, it decreases the cost, it builds trust. These plants, one is actually being commissioned, I think, this month, and the other is being commissioned in October. So in 2018, so this took 5 years, and this took 6 years. So and you see that how they will, for the new projects, how they evolve and so on. But it just gives you an idea of how realistically it takes to build a project. Another reason why I bring this is because it's not the same level of detail that you need for designing an operation. For proposing a project, a proposal here, done here, done here, then here. The closer you are to financial closure, then the power plant design needs to be very specific, and then it's locked. This is it. This is what we're putting money on. At the very beginning, you just have the pre-design. Let's see, like, this is if this is interesting. You know, there's not so much level of detail into the components and so on. And actually, during construction is where you have the final one, because it's what you can test. You know, like, sometimes, most of the cases, this is engineering, what you design for, it's not what really ends up being like. So of course, here you have to have models or operating system simulations that are really detailed to the level of required here. So depending on where you are in the process, you will require a level of detail that is different. And depending who you are in the process, you require a level of details for different parts of the systems, depending on what your purpose is. So the financial institutions, of course, they need, what they care the most is the financial model, like putting all together the revenue streams, the cost streams, and so on. The heat exchanger owner only cares mainly about the CFD and computational fluid dynamic calculations in the component and the material and so on. So you see, like, this is, just so you know. So when you ask, I had a question before, what's the best software? It depends. What do you sell? Do you sell heat exchangers? Do you sell the storage? Do you care about the system? Do you care about who pays for it? So there are different software for all of this, of course. This is the same, but just put it together like in steps. So for a general, so this was the case of Morocco. If you look into another, this is general for, in average for all power plants, CSP plants. From project assessment to its operation, this is what happens. So you have like 3 months of pre-assessment at first year, where you have a pre-feasibility and project definition. This is where I work the most, actually, as an engineer and a consultant. I'm like in the whole pre-feasibility, project design, helping define contracts. Then you have the real engineering. So let's start, if you get a project, you start construction. So construction, final engineering, getting all the equipment, the civil work constructions, the commissioning, which is real, making sure that the plant already in the last stage starts performing as it should. So the heliostats are doing what they're supposed to do. The receiver is working as it's supposed to do. Usually the contract between the constructor or the engineering firm and the development is like, once you can certify that everything worked as the performance model, the simulation, for 6 months or something, then the constructor doesn't care anymore, the contractor, and basically gives hands on the power plant to the owner, the operator. And this is the other phase of the project, which is the operation. 30 years, 40 years, you name it. This is more or less like the real ecosystem. You have people that own land. You have the general contractor who builds projects. You have the authorities like Masen who release the tenders, set the permits, etc. You have the off-taker, which is the one that buys the electricity, which is of course key. The main key here, of course, is the project company, which is what we call like this one. The people that build up the project. The project company is the developer together with the technology owner, together with the engineering firm. There's usually a consortium of different actors. They want to win the project. But they interact with different actors. They interact with the landowners, with the contractors, which is sometimes one of them, with the authorities like Masen, with the off-taker, which in this case is also Masen, with the grid feeding, which is in this case ONE, for instance. The operator, which in this case in Morocco, the power plant owner is Aquapower with Masen in a share. And then the operator is a subsidiary of Aquapower, another company that Aquapower has for operating assets, for instance. So then you have the creditors, the ones putting in the money, the debt to build the project, and you have investors which are also putting the money, but they are equity, they are owning the plant. These ones doesn't care about owning the plant, they just want their money in return with their interest in 20 years. And then of course you have people like me, which is like, you need consulting firms, and all of them need in different stages, for instance, like for auditing, for engineering, for due diligence, they also just to check. And of course, there is no project if no one sells the heat exchangers, the receivers, etc. So you need people that sell the components. But all of them, again, are needed in the whole ecosystem. All of them will design plans or check the design of plans, and all of them have different interests in terms of how they make money. And that makes it, on that side, complex. But then the other side, I mean, putting everything together is that when you build a plant, let's say, given already you know all the actors, which makes it already complex, and the contractual relationships between them now, you have objectives. I mean, as a designer of a plan, or as a consortium, if you want to build a plan that is as low cost, high profit, and creating a lot of local content, like local economy, right, as possible, but at the same time it should be very high efficient, with high availability, easy to operate, like so that you can easily operate, ramp up, ramp down, depending on the needs. And at the same time, you want a plan that it's like low intensive in terms of emissions, low intensive in terms of raw material, etc. All of these objectives, like financial objectives, technical objectives, environmental objectives, could be contradictory. Like usually, the plan that is the most efficient, or the component that is the most efficient, is the most costly too, and vice versa. So there is always a trade-off. And there is where, as asked before about multi-objective optimization, that's where this comes in place. If you can quantify this in one objective, this in one objective, and this in one objective, then you have a three-objective problem here that you can also weight what is more important for you at the end. But typically, this is it. The plan that makes more profits. I mean, that's probably the one you care the most about. But you need to combine that with meeting minimum technical requirements, which then must make sure that you at least guarantee that, and some environmental requirements. But this is a multi-objective problem then. So, I'm get tired of holding this. So from a technical perspective, you can quantify. I mean, if you're going to design, then you need to quantify your objective. So we want the plan to be the best technically, the best financially, and the best environmentally. That's what I said, right? That's obvious. But then to calculate, as an engineer, then I need to put numbers on that. What's best? So you have objectives that are technically, and you can quantify them. The most obvious ones are the yield. So we want a plan that, when I talk about the yield, it's basically that produces as much energy as possible. So that the yield is quantifying the gigawatt hour energy or electricity that I generate. That could be something that I can measure, right? And as an engineer in an optimization problem, I can maximize that if I want to. So I can evaluate different designs to check which one gives me most of the energy. Another technical factor is the capacity factor. Depending on what you design the system for, you might be required to meet a specific capacity factor. And I mentioned this before, but I didn't explain what it was really. But the capacity factor is a measure, or it's a quantity that measures how available my system, my plant, is throughout the year. So if you put it in perspective, if you look at, I hope you can hear me. It's basically the ratio between the yield, so this thing, right, divided by the potential yield, the theoretical maximum, if I was operating at all times at the maximum capacity. Right? Depending on the technology you have, this capacity factor varies. So let's see, just so that we don't make this boring talking much, I'm actually tired. So what is the capacity factor for a PV plant? Just random number. Okay, CNEP, because you won the contest today. What is the capacity factor for a PV plant? No, but where is CNEP? Zineb went to the restaurant already? Okay, Zineb, so what is the capacity factor for a PV plant?
Actually, I don't really know the answer because it's not my field.
So, yeah, but it's around 30%. I mean, just think about like, it's a matter, the PV plant operates only when there is daytime because there's no storage. And even when there's only daytime, they maximize output only when there's the most irradiation, which is solar moon. The rest of the times they're producing less or non-producing at all. So the capacity factor for a PV plant with tracking mechanisms maximizes at 34% with a tracking mechanism. Whereas in a CSP plant, the capacity factor could be 80%. I mean, it depends, like you saw before in the image I showed to you from real data. The plant was operating at all times because we had storage. So like this is a measure that I can quantify and I could build the trade-offs, you know, how much more it costs to have a capacity factor plant that has higher, I mean, a plant that has higher capacity factor, or how much more do I need to invest or so. And it could be an objective, so something I can quantify. From an environmental point of view, one simple objective, of course, is how much tons of CO2 does the plant generate? And I could design a system that minimizes this. Of course, in the case of renewable systems, this is zero. I mean, or most of the systems is zero. I mean, like, at least directly zero. Indirectly, when you look into the life cycle analysis, it might not be zero. I mean, you know that there is energy that was used to create the components, which might not necessarily come from renewables and so on. But at least when it comes to the actual power plant, this is usually zero for all renewables. So it's not seen as a real objective of design. We all depart from the fact that a CSP plant is 100% carbon emission free, same for PV and so on. And then you have financial, different objectives. These two are not objectives on their own. One is Capex. Capex is investment. The Capex is not an objective alone. I mean, investment is just what you need to build a plant. Of course, you can design a plant or try to find what is the cheapest plant. So then it becomes an objective because to meet some technical, so usually like, let's see, my target is an annual yield of 400 gigawatt hour. Then if that's my target, I can make an optimization problem of what is the cheapest plant I can build such that meets that target, for instance, right? Then it can be an objective. But usually this is not an objective because at the end the Capex is just, I mean, the money you need to get to your real objective financially. Same for OpEx, the actual running cost. And the main objective is usually in terms of profits. How much money I make. Not how much money I invested, but how much money I get back from what I invested. Profits are measured, and this is not renewable or anything. This is just financials, project evaluation. So not on a specific field of this, but I just wanted to teach you because you design for this. I told you before, this is a business. Most of the actors design for increasing their profits. Profits can be measured in terms of internal rates of return. So for the money I put in, how much I get back at the year 20, for instance, or at year 10. You want to maximize that. It's the only reason why everyone is here, like to do this, unless you're like a researcher, which I also are. So for the sake of doing stuff and because you like it. But anyone else is just here because they need to make money, because they work for companies, because and so on. So we can define two things here. One is the levelized cost of electricity, which maybe you're all familiar with, but the levelized cost of electricity is a ratio of all the cash flows in the discounted cash flows in the lifetime of the plant divided by all the energy, discounted energy, in the lifetime of the plant. So theoretically speaking, the LCOE, or levelized cost of electricity, is sort of like what is the constant price that I need at money value today so that I can break even, meaning that so that my investment meets my target goals, usually, my profit goals. Whereas in terms of IRR, it's just directly the profits. It doesn't give you an indication of the, I mean, it's not energy per megawatt hour. a project is acceptable, of course, if the IRR is at least what the investors want. Otherwise, then why would they ever invest here? They just go and put their money in the bank then. Maybe that pays off better. But these are notions of basic project evaluation. Then if you know these notions, coming back to this problem, of course, you want to design, most of the cases, a plan that is as efficient as possible, but as profitable as possible, with emphasis on as profitable as possible, because everyone is here for making the money. Otherwise, this is not viable. I mean, why would you build something that is not sustainable in the end, that you cannot pay back or so on? And you need to put numbers on that. You can quantify all of these objectives by discounted cash flow theory. That's just financing here. Now, if you know what an IRR is, then basically the difference between PPA, or what you read in the news, power purchase agreement price, and LCOE is that the power purchase agreement price is the price at which the IRR, the profit level, is greater than the weighted average capital cost. And this gets complex because it's financing, but the LCOE is calculated with WACC, basically, the weighted average capital cost. So it gives you a notion. But the PPA is the one that when you put all the different debt mechanisms, the different where the money comes from, the different debt conditions and so on, tells you this is the price, and this is the way the price scales. Like year 1, it could be 100, but year 2, because it's inflation, you pay 102. Year 3, you pay 104, etc. This is the price that you need to bid for, usually. What you're asked as a proposal offer is what is your bidding price. So this is connected to, from a project proposal perspective, if you are the project company, the one there in project proposal, you put a bid such that can guarantee the investment or the profit requirements that are acceptable for everyone putting money in the project. So you need to bid for the price that's such that can guarantee that investment back. To do that, then, there is a process. We use one. This is, forget about the word DICE up there. So there's a Powerplant modeling process there that you can follow. So one is, what are my design objectives? And I told you, depending on who you are, you might have different design objectives. But let's say your design objective could be minimize this LCOE, because of course, as you minimize the dollar per megawatt hour, the more competing or the more competitive your project is for Masen. For instance, like the cheaper your offer is, as long as it can guarantee some technical conditions, that's the one that's going to get selected. So usually that's an objective. So minimizing my LCOE, perhaps maximizing capacity factor, because you need to comply to a specific capacity factor. Maybe Masen says you need to be 80% available. So of course, then the problem comes into finding a power plant, the best power plant that is able to deliver the cheapest LCOE, the cheapest price, dollar per megawatt hour, compare as trade-off with the availability of the plant. And you will see there's a trade-off. So to do that, you need to know a specific location or location-specific data. You need to build cost models for that location. Like it's not the same to buy something here than in China, or vice versa. To consider labor costs here than in China, or vice versa. To set input limits to the optimization problem, because if you're optimizing, of course, you need to provide boundaries to what are you optimizing with regards to. Is it the size? Is it the size of the tower? Is it the size of the solar field? Is it the number of heliostats? Is it the position of the heliostat? Is it all of them, which is usually the case? I mean, you just optimize for every single technical component in order to quantify in that objective. And then with those inputs, then you have a model process where basically you size the plant, and that's done at a specific design point, which is usually, coming back to my very beginning of the lecture today, a design point, which can be solar noon in the equinox. So for that specific time, I assume an irradiance of 850, irradiation, of 850 watt per meter square, and I consider a solar multiple of whatever, the design that I put 2, and a tower of 180, whatever. I size everything, and I calculate all my plant, like this is my steady state design, which means like not dynamic, just like at this point, this is how the components should be sized for meeting a specific. So if I want a 100 megawatt electric plant, and this is the design condition, this is how large the field should be. This is basically what it is. But that is only true at that point. So in solar systems, in renewable systems, a design that is only at design point is useless, because design point is only met once a year. most likely that will only, like, unless you have like a lot of storage and you can control that, these conditions will never be met again. So in designing the systems, you need to have an annual simulation, which is like you need to use data hourly for a typical year. Because only one point of that was used for sizing, but in reality, the performance, which is how the plant really acts for a given size, depends on the weather conditions, because this is solar energy. And solar radiation and position and everything is varying at all times. So the performance, the output of the plant will vary at all times. Once you have the output, let's say the yield, like what I talked before here, so the yield could be calculated already here, right, at the annual performance. Then you can calculate the other indicators that I mentioned before, like the LCOE, because you have the yield, you have the cost. So you can calculate the profits, you can calculate all this stuff. If you start varying the size of the components, repeating this process iteratively, you're going to end up with a power plant that will meet your objective, minimizing LCOE, maximizing whatever your objective was. So designing a plant is a complex process. The level of detail required, what I want you to keep is this. So it's a complex process. The level of detail required depends on where you are in the phase of the plant. Is it at the very beginning, pre-feasibility? So do you want to spend like 4 months doing this process if you're only not even sure you're going to get anything back from it? No. Do you need to build a detailed cost model if you're only at the beginning? No. You only need like basic assumptions to get something that allows you to estimate if this is interesting for you. But if you are at the very end of the project, then this should be very detailed. Like the cost model should come from supply offers, you know, like from real companies and all this stuff. Labor should come from real subcontracted people, etc. Otherwise, it's just assumptions and so on. So all of this can be done. It needs to be done, and it will be done at different level of details depending on where you are in the project phase. And the objective will be different depending on who you are. Like some will just care about maximizing my Capex from the solar field, meaning the requirement investment in the solar field, because I sell heliostats, so all I want to care is that they pay me more for my heliostats. For instance, I'm just saying, like, so just keep this in mind. So like, you have different objectives. If I am going to talk about the main processes here, so 1, sizing, 2, annual dynamic simulation, 3, calculation of the objectives, like LCOE, and 4, the optimization. I don't know how we're in time, but when is the break? 3:30. Okay. So do we have questions now before I get into the other poly model? Oh, I have it in the system. So here, right? The last one. So before I start into the details of modeling, just see what's the back. So someone of your colleagues here asked, for Masen, it took like 6 years in order to conclude the building of one station. What I'm asking is, according to your knowledge, sir, thank you for sir, could it take less to build the same kind of station? 6 years is not too much time, but it's time. It is a lot of time, and nowadays you are required to have, from the very first time you're given a contract to the injection of electricity into the grid, usually 3 years. Like nowadays, like some of the people awarding contracts, like electricity contracts, tell you, okay, the plant needs to be ready by 2020. Forget about it, it's your business if you do it. If you don't do it, then this contract is no longer valid. So of course, like all the one in the engineering, the contractor firms, everyone is like in a rush to deliver to get the price that they were secured. So definitely, I mean, this is something that you just decrease. It's just a learning curve. At the beginning, it was impossible to build. There was no such know-how in Morocco. So it would have taken this much. For the next projects, it will take less and less and less. It will become more. I mean, like nowadays, for instance, you are here. 6 years ago, I'm quite sure almost no Moroccan was aware of renewable energy engineering in their schools. So like, it's the same. I mean, like nowadays, you guys will be the ones that in the next 2 years, there will be more projects, and you will be with the know-how in-house to promote them, to build them. This was not there before. It's the same. It's just an ecosystem. And the same as the know-how is there technically, same from the finance part. Now banks know it. Banks can go towards that and see it. It's a reality. 6 years ago, then banks were skeptical. It's like, so this is like, you know, a new technology where you heat up to 600 degrees. Now it's too dangerous. Like, let's build a coal plant. It works for 60 years. So like, you know, this is a whole thing that's changing. So time will reduce. However, it produces less. Why NUR 1 took more time for planning than NUR 2? Just what I just said. And this is a matter of maturity, experience gain. I didn't get the reasons behind different costs per megawatt. So the reasons are a combination of maturity level. People now trust. The industry is more experienced. Masen is more experienced, and the banks also can. In the very first projects, the banks needed to consider this as a more risky project. When you consider something more risky, basically what you demand is a higher interest on your loan. Nowadays, it's just like less and less. I mean, they see it as less risky. So of course, the combination of all of this, experience gained from all the different actors, bring down the cost. In your opinion, why Masen doesn't develop NUR 1 and make the storage like NUR 213 as 7 hours, which are things that had been added for develop the number of hours of storage? So why not use concrete for storage FB calorific capacity? There are a number of reasons here. I mean, concrete sounds promising, but technically speaking, as I said before, it's not as maneuverable or as reliable as the salts, because the salts, concretes in the long term, first there is a question mark on their durability. It's the same concrete that is expanding and contracting all the time, and we don't know if that will actually last for the 30 years. Although that also applies for the salts. But the thing is that the salts are less exposed to this thermocline effect, and they don't have thermocline effect, and also to expanding or contracting. The salts are just getting hot, because they are always in the same state, and they are just going from, like if you put water from, I don't know, 10 degrees to 40 degrees. We know how to do that. It's not a big deal like there. So that actually molten salts behave like water in terms of the pumping and so on. That's the reason why we go for salts. And also, they can reach the temperatures that we want to. Concrete, no. At least not the concrete stuff. So storing energy in concretes at 600 degrees is not viable. You will need like special concretes, for example, but not the common concrete. And then in terms of the storage capacity in hours, I told this before. I mean, this was a request. Like at the very first project, Masen deterministically asked for a 3-hour storage. Then they realized that maybe they gain more from having more power, more backup. So in the last 2 projects, it's 7 and 9. What will be the next? I believe will be 5, because I've been working on them. But it's something like that. I mean, it depends. What's going to happen if we add centration technology to a PV plant? If yes, there is no dangers of the glass of the PV plant, and if we will have an avalanche effect of the election of the semiconductor. Okay, so this is not, this is a PV question, and I guess centration means like concentration. There is something called, I don't know if you went through it yesterday, but you can also concentrate and have a PV in the focal spot. Of course, that will increase the energy on the PV cell, and that will make it more efficient. But the costly part of CSP is actually the mirror. So you're adding a lot of cost to something that is cheap. And what you get back in efficiency is very low, because the efficiency of the cell is limited to the actual band gap, to the actual technology you're using. So I don't know how to the level of detail you went yesterday to PV, but basically, in order for an electron to move to, and to generate current, it just needs a specific amount of energy to pass the band gap. If you give them more energy, that energy is just wasted. It creates the same current. So that makes sense. So that means that all these cells that are used with concentration, which there exist, are just a mix of cells that, and I don't know if I'm getting too technical here, but it's a mix of cells that require a different spectrum of the light. So at different spectrum of the light, you require different band gaps. So like, for instance, you put in front a silicon one, which is the common one that everyone uses, and then behind that, after that one uses, if you expose it to a light, that one uses an amount of energy, 1.1 electron volts, and then a spectrum, a part of the spectrum. But if you put another cell behind, which is made of gallium, that will require 0.3 electron volts, and this I'm actually making it up. I don't know how much the gallium telluride needs, but yeah. And then it will require another amount, and then another part of the spectrum. So you can pack them all together and create these higher efficient cells made of different cells, actually, for concentrating PV. This exists, but this is not what I'm teaching about here. But there is CPV, which is concentrating PV, and actually in Nord, you can see a 1 megawatt system operating on CPV in Warsaw. I didn't understand the difference between LCOE and PPA. It's not obvious, and if you're not in finance, it's not actually obvious at all. But LCOE, it's disconnected from the cash flows, like from the money, the debt, the type of debt, and the amount of equity interest that you want to make, the profit that everyone wants to make. It's literally the amount of money put in throughout the lifetime, discounted to today, or to a specific year, divided by the amount of energy produced, discounted to today, or a specific year, using as a discount rate the WACC, which is a weighted average capital cost. It's one way of putting it together all the financial model in a single number. But this is not precise. So the one that is really precise in terms of cash flows and everything is the power purchase agreement price, which is the one you bid. But when you talk, I mean, as a student and so on, you can just relate to LCOE, which is the ratio of cost divided by energy, and it gives you an indication. However, I mean, you keep in mind that when you talk about LCOE, you don't make a difference in terms of when is the energy produced, for instance. If you start comparing the LCOE of a PV with a CSP, and you tell me, yeah, the LCOE of PV is better because it's $25 per megawatt hour, and the LCOE of CSP is 70 or 90, then yeah, that's true, but you're comparing pears to apples. I mean, like, again, the whole purpose of today is that you realize that they have a different value. So you should compare then the CSP with another plant that is able to deliver 80% capacity factor, that is able to provide electricity at 9 p.m. then, because they serve a different purpose. And this is actually not easy for everyone in the business. I mean, some investors only look at LCOE, and they don't necessarily understand why you cannot directly compare the LCOE of a wind farm with the LCOE of a nuclear plant or whatever. But of course, if they are only looking into the profits they get back, then they don't really care when the energy is generated necessarily. So that's why in the ecosystem, we have the system operator, we have Masen, who defines, yes, we cannot just have only PV and have a lot of energy at noon and then no energy in the night. We need this other technology, even if from an LCOE perspective it's more expensive. But again, LCOE is not 8. LCOE doesn't show you the value behind CSP or the value behind a dispatchable technology. And PPA is actually the price you bid on, which is associated with inflation and escalation factors. Why should the PPA price have a minimum value? Well, let's see. This is a competition, right? I cannot do this. This is, if you remember the process that I showed before, this is a competition. I mean, you are request to propose a plant with a bid. And if Masen gets 10 bids, one is 10 times higher than the other, which plant will they bid? Which plant will win? They will build the cheaper one. So that's the reason why we designed for the minimum PPA. We're looking always for the minimum PPA that still gives us profit, everyone in the plant. The lifetime of troughs is generally 20 to 25. After this period, how can we recycle? Okay. So first, not true. The lifetime of a CSP plant has been proven to be 40 years, and the question mark is even more. The thing with CSP is that the degradation is close to zero, relying on the fact that we do constant maintenance. Like for a coal plants live 40 years. This is the same. The CSP plant can last the same as a coal plant. Now, what you compare here, 2025, is the contracts. So the electricity contract usually is no longer than 20, 25 years, the first one. But then you have an asset, power plant, in which then you can get a second electricity contract at a way different, lower price or whatever, because you already paid investment, so that, and the plant is still there. So in terms of lifetime, a CSP plant can last 40 years. Now, a PV plant cannot last 40 years. And the reason being is that the degradation of modules is such that in year 25, usually for all the technologies that we have commercially available, in year 25, the plant produces 80% of the installed capacity. There's a degradation in materials. This is not like because of the way we clean it, because of the way we operate it. The material degrades. And so that's why this is another thing that has been really a problem for CSP, is that CSP plants are giving contract lengths of the same length than PV. But in reality, a CSP plant, of course, will be able to offer a cheaper price if we were able to secure a contract for 40 years instead. But we don't. So you need to make a financial case with 25 years, knowing that maybe that you will have an asset that will actually live longer. Some take the risk, and I've been in projects where the developers take the risk to bid in something lower than what the profits they expect because they believe that in the years afterwards, they're gonna get a second price with another people that's gonna make them more money or compensate for what they didn't make in the first 20 or stuff like this. But a PV, no, PV is actually built for 20, and at 20 years or 25, it will be decommissioned. So like you will recycle the materials. But coming to the recycle question, basically, there's a lot of recycling possibilities in CSP because all of the equipment here, it's mainly metallic and concrete structures. So all of it can be recycled. Now, in reality, as I said before, the first projects online came in 2006. So this is not a question that we know how to handle because from 2006, from the very first projects till now, they've only been then 10 years, give or take. So we don't know what we're gonna do when the plants are done in 40 years. I mean, it's only 10 years. Same for PV, actually. A lot of people are wondering what will happen with PV, and there we're reaching closer. We're closer to the deadline because some people say, for instance, depending on the technology, like cadmium telluride, I don't know how far went you into technology yesterday, but one of the PV cells is thin films. So thin films, which are mainly cadmium telluride, are supposed to be aggressive or as a media. So when the time comes that we need to recycle that, I'm not sure how well we're going to do with that, but we'll see then. Let's say. Can we have those interesting slides? I hope so. I don't know. I think you will. Excuse me, sir, I'm confused. What do you mean by nominal factory? So whenever I mention nominal, like nominal in engineering means the design point. So the nominal rated power means the power for which this component was built for. So my design conditions, so as an engineer, I need some boundaries, right? It could be not only solar. I'm just saying here solar because it's what I do, but at irradiation of 850 with a wind speed of 4 meters per second with, the position of the sun at solar noon, then this component delivers 80. That's the nominal rated design condition of that component. That's what I mean. But with the moment the conditions are not like this, then the component doesn't necessarily will behave as a nominal. I mean, it will provide less or more, etc. And that's why in renewables, it's very important that you don't only look into the nominal point, but into the actual year performance, because the nominal point will happen probably only once. Is there a specific technology that we have to respect if we want to make a power plant modeling? I don't follow the question, but there are different software, and depending on where you are, again, you will use one software or the other. And depending on what you want to model, you use one software or the other. In DICEP, how can the LCOE be an indicator? So regardless DICEP is just a tool that I developed, but forget about DICEP. The LCOE itself is an indicator because you, as again we said before, you want to build a plant that is competitive. And competitiveness is measured today in terms of LCOE. It's an indicator that in one single number connects cost and production. So that's why you want of course, something or a plant that gives as much energy for the lowest cost. This is just intuitive. So that's why you're always looking into this metric. In your opinion, what is the key to success in the energy field in our time career? I don't know. I'm trying to find that out too, I guess. So I guess you ask for any. I was asked this in the lunchtime. There is no secret. You work hard in any career you have, and as you like it, you work hard on it because it will be natural for you to work in it because you like it, and you will succeed. I think there's no secret to this. Thank you for the presentation. Oh no, thank you. My question is there a chance for internship? I don't know. Awesome presentations with technical and pedagogical. How can we good speak? Oh, thank you. Internship period in Sweden, thank you. How does the type of technology influence the duration of building a CSP station? It's true. Of course, the more mature the technology is, the shorter you will need to build it, because we know how others did it in the past. So it's just an experience. So because troughs have been built for many years, today they take shorter time to be built than a tower technology. But because of experience. For the person who wants to get a chance for internship, I didn't say this, but okay. So we have a break at 3:30. So before we get there, just going through these processes very quickly, because, well, this is the main core, but you will not get all the thing from just a lecture today. But so how do you do Powerplant nominal design? And this was connected to a question before. You have a number of, first you need to understand the system. So you need to understand your system. So let's say this is a tower plant, right? In a tower plant, you have different blocks that you can distinguish. One block is the collector part, the solar part, so how I collect energy from the sun. One block is the storage and heat transfer fluid part, which is how the fluid that gets hot, what do I do with it? How do I design that? And the other block is the block that converts the heat from this fluid into electricity, which is the power block cycle. All of them can be designed specifically. All of them have sizing design questions independently, both at subsystem level and also at component level. So if I look at solar field, of course I could ask the question at a system level of what should be the solar multiple, the concept we were discussing before. But if I go into detail, then I could decide how large should the heliostat look like. I mean, how much mirror area should I have per heliostat? How large should the receiver should be? How should the geometry of the receiver be? How tall should the toll be? Those are questions that I can answer. I mean, these are design questions from this side. In this side, the same. What should be the rated power, so the thermal power of my receiver? How much storage how large should the storage tanks be? What should be the effectiveness of my heat exchangers here? Meaning, how large should they be? Of course, you know, like in any heat exchanger, the larger the area, of course, they will deliver more energy. But the larger the area, the more costly they are. So, and then here the same. You have how many stages should I have? How many preheaters should I have? Which type of cooling condenser should I have? Air cool, dry cool, a combination of. And then if you put it all together, this is a very complex problem. All of them you want to optimize. All of them you want to choose a size for everything. So again, in the solar field, you can size how many mirrors, the type of mirrors, like reflectivity, the height of the tower, the storage capacity, the tank specifications, you know, which type of insulation, why, the way it should operate, the minimum levels, the capacity of the power block, you know, maybe 100 megawatt. Is it 100 megawatt that I want, or 20, or 150? Is there a difference? So this is what we call nominal design, because for a given location, for a given point of the day, of a year, like say solar noon, what's a sat, that gives me already the sun position, and that if I say summer solstice, it gives me already, I can read what is the typical irradiation or summer solstice. So solar noon on the 21st of June, this is my design condition. And for that, if I say I want to build a system that delivers 100 megawatt electric, for that specific condition, I can size all of this. For a given size of heliostat, for a given size of receiver, etc. But this is usually a question mark though. How much should I size them and so on? Once I've sized, say by size I mean I have 1400 heliostats, the receiver is 500 megawatt thermal, the storage is 3000 megawatt hour thermal, the power plant is 100 megawatt with 7 stages, the power block. This is size, I decided that. Then I can run an annual simulation. For that given size, for that given type of equipment, I can then vary my boundary conditions, so it's no longer solar noon watch the sat, but now watch the sat, but at all times of the day, all times of the year, sorry. So you have how, this is a week, so the given plan that I designed, which was 100 megawatt and so on, this is how it would operate. So here you have in black prices, in yellow irradiation, or well, not irradiation, here's the thermal power from the field, which is of course connected to irradiation, but and then you have in red the storage, and in blue the actual production, like from net production, so delivered to the grid. So this is what you're interested in, because if I design for 1 point, I will design, I mean, let's say Wednesday is the summer solstice, or Tuesday. So I will have designed for this point, so which is like these conditions, this and so on. But in reality, the plan has like, it's exposed to all of this different variation, right? So you see, you wanna see how the plan performs in a real weather data file, sort of. And then you have, if you combine it with prices, which is here in black, of course you want to build a model that allows you to estimate how should you use your storage. So what we see here in this type of models is that for a given price strip, so data, for a given weather data, for a given size, this is how you should operate then. Because what we see here is that if these are the peak prices, you're saying it's like, use the storage smart. I mean, like dispatch when the prices are high. So you see, like in a day like this, we are collecting low energy, we don't reach the full tank, but then the model says, it's, again, I mean, collect here, don't sell here, so you see blue is 0, go online at this time where you have a peak, go 0, and then go online again when you have this peak. So all of this you want to do when you model. Like, so I'm building these models, of course, it's complex. The outputs from this process tool, then you have a specific hourly production. So at every hour of the year, you have an estimate of power, thermal power in, thermal power out, I don't know, everything that's happening in the problem. With that data and a cost model, and the cost models needs to be as detailed as you want to. So a cost model could be as simple as you say, the CSP is $3,000 per kilowatt. That could be a very simplistic model, and then you multiply by the kilowatt install, and then you have the cost of CSP. But if you want to build a real detailed model, then you have to have the cost of the power block, I mean the cost, the investment, it's a function of the direct cost plus the indirect cost. The direct cost is a sum of the cost of the power block plus the solar field, plus the storage system, plus the receiver system, plus cost connected to how I had to work on the site to make it flat, for instance, to cost of the balance of plant, to cost of the tower, etc., etc. And the more you go in detail into the project, this needs to be more and more detailed, because this drives the whole output. I mean, you're calculating LCOE, remember, or PPA price, which is a function of the cost. The cost assumptions, or data, I mean, together with the economics in terms of the financial metrics, the interest rates that you have from the different loans, the equity rate of return from the investors, etc., will allow you to calculate, together with the output from here, the yield, these metrics, which is the ones you want to calculate at the end. And then you do that for a number, I mean, you can do that for one specific plant. The one I told you before, the one is 100 megawatt with, I don't know, 8 hours of storage, and this size of field, which is like, I don't know, 550 power from the field nominal. But what if I start varying that? I mean, I could actually look into a plant that has 600 rated power with higher power of production, like 200, etc. And then if I do that iteratively, I'm going to end up with, this is a multi-objective problem. So here what I have, it's my objective 1 was maximize my profits in terms of IRR. And what I have here below, it's minimize my Capex. So the question that I'm answering, if I use these 2 objectives, is an example, but is what is the plan that gives me the more money for my investment, right? So what I see is like, most likely, the more you invest, based on the type of conditions we set for the problem, the more you invest, the more you can get back in terms of profits. But the more you invest, it's also the higher the risk in terms of whether, I mean, what happens if you actually don't deliver? What happens if it doesn't happen, right? So it's a trade-off. I mean, for this amount of money, you can find a plant. Each point here is one power plant, meaning a specific tower size, a specific rated power, you know, like 100 megawatt or whatever. So each point here is a specific design. And then each point you can say, for this amount of money, the best plan will be plan A. That's what you can say from this. Because for that type of plan, you get the best money out of it. Same, if you don't have that amount of money, but you have 5 times that, then build a plan like C. You get more money from it. So it's like those type of questions you get from this is a multi-objective optimizer. So you have here how these are different power plants, right? And of course, the ones that give you more profits are the ones that are better designed from a solar field efficiency point of view. So you see how the solar field, the ones with the higher solar efficiency meaning the better collector field, the lower losses from the lower cosine losses from, and the ones gives you the more. I mean, this is obvious, but this is an example. So A, B, and C are all plans that are optimum, depending on who am I. Because if I am someone that is willing to, the EPC, the contractor, and I just wanna, if I was given 600 million, but this plan meets the same requirements than this in terms of install capacity or whatever, then this is optimum for me, or because then this is that it meets the technical requirements, but it's cheaper, so I get all the margin for myself, like for us an EPC company, and vice versa. Whereas like building a plant like D makes no sense. So because D means that if you have that money, you can build a plant like C here, which for the same amount of money gives you more money in profits. I mean, like investment, like profits, return. And similarly, for the same return, you can build something at lower capex, a lower investment. So that's the type of analysis you want to build, so that you can make the decisions on where to go for and so on. And they are very subject to the level of detail you put into all these steps, and they are very subject to the assumptions you make, etc. So this is an example before we just have a break. So let's say I have a power plant in Uppington, which is one of the best regions globally to build CSP. So this site is about like 2,800 kilowatt hour per meter square DNI. And then we have this profile. In South Africa, we had this in the last tender, which is like you were paid 2.7 times more in the evening hours, which is a way for the government to say, we want plants that deliver in the evening hours. I mean, because if you only build one that builds in the day, you miss this peak price, right? So if you repeat this process, then you can kind of end up with different type of plants. So remember, in these plots, each point is one power plant. So for instance, if you look at what they are here, so these are my objectives. For a given capex, I want to find a plant that, given this resource and price, maximizes my profits, right? So I'm interested in the plants in the front. Now, I can see different trends. For instance, as I increase the capacity, I mean the power block capacity, I see that I definitely need to invest more because I'm building a larger plant, but I'm also gaining more profits. And if I look into the same picture, because these are the same power plants, but now looking into what they mean in terms of size of the field and size of the storage, then you see that all the optimum plants, like here, end up being like with a storage capacity of 4 hours or stuff like this. And that was obvious. We're gonna get that because look at the price curve. You have a differentiation of 3 times being paid for 4 hours in the evening. So of course, what the optimizers should have suggested is build a plant that only operates in this price. And if you look in the way you should operate, yeah, well, this is also, I don't want to get into detail, but peaking, meaning don't produce in this day, just in this time of the day, just produce in the evening. And then all the red points are peaking plants, the blue ones are just produce as you have, you know? So like all these questions you can answer from optimization. And this is an example of optimization. The way you size the power block, the solar field, the TES, the way you choose, the TES is the storage, the way you just choose which components and so on will have an impact directly in cost and in the metrics that you're calculating. And if you start varying the price, the way you are paid, one optimum for this, which was this plant with only 4 hours of storage, is no longer the optimum in a price scenario like this. I mean, the same plant A will not be optimum in a scenario like this. It will be somewhere here. So it's suboptimum because you are paid differently. And if you are paid like this, which is same price and no price in the evenings, for instance, then another plant will be optimum. So all the conditions matter when you are designing. And every location, you have a different solar resource, a different way of being paid, etc. Here you have an example more specific. So like plan A, for a price like this, with that location, like .dni, maybe the optimizer says, the best is a plant with 110 megawatt electric, only 4 hours of storage, solar multiple of, I don't know, don't look into solar multiple. Let's say a perch mirror area of 1.3 million meters square, tower height, etc. You can look into this. And each of them is a power plant. It's just different. I mean, B is a power plant that is almost like a base load plant, 14 hours. So this comes back again to the question of How large should it be? What's the optimum size? Well, it depends. It depends on how I'm paid. It depends on what the market wants. It depends on what are the drivers behind this. And I think that's actually almost the last slide for today. But before, I want you to keep this in mind because I didn't go into detail into this today because it's only one day of CSP, and you must be tired of hearing my voice. But one thing of CSP that is not like for other technologies is that in CSP we are converting solar energy into heat. Mechanical structures, components that are exposed to heat or that are getting hot and cold at all times are exposed to transient effects. As an engineer, I need to consider transient effects. And transient effects translate into two main things. One is thermal stress. So if something is cold on one side and hot on the other side, for instance, like a tank. The tank is hot on one side because that's where the salts are in, right? And it's cold outside because it's just the air. That component is suffering thermal stress, meaning that if you look into the mechanical structure of the wall, you will see how the well, I don't want to get too technical. The stress is suffering is such that it wants to break because on one side it's super hot, on one side it's cold. And this will vary cycling. As you fill the tank, it will be more the part that is hot or cold, etc. These effects you need to consider on design and also in operation and so on. And the same is with thermal expansion. When something is heated, it tends to expand. It will expand. That's why in bridges, you see the connectors. I mean, like the bridge, before you jump into the bridge when you're driving your car, you have like, right? Because in the daytime, the bridge will want to expand. The same happens in CSP. You're talking about technologies that are getting hot. During daytime, while they are heated, they will tend to expand. In the evening, they will tend to contract. So you need to consider all this when you design. You don't necessarily do this for other type of technologies, but for CSP is key. Okay, so let's make our last round of questions, and then we have our break. Then I will just show some simulation quickly, okay? Let's see. Okay, so we only have one question. So TES is an acronym of what? So TES is thermal energy storage. Okay, so I could refer TES to storage the same. But in your opinion, why most CSP uses ranking thermodynamic cycle in turbine operation? This comes back to one of my first slides. I don't know. It's a matter of cycle efficiency and meeting what the system can give me. So I think if I go here, maybe. Yep. So you remember, I mean, for those that are mechanical engineers, you might know Carnot efficiency and so on. If my system is able to reach my collector system, my solar tower and so on, able to deliver, bring a fluid to 600 degrees, then the most efficient cycle that I know of today that can operate at 600 degrees is a steam cycle. So that's the reason why most of them are steam cycle based. If the system will be operating instead of 1,000 degrees, then this will be more like a gas turbine cycle, etc. But the reason for the steam being the most common cycle is because steam cycles are the most efficient technology when you're operating between 300 and 600 degrees. And that's where all the plants that we have today, or the know-how that we have today, materials and so on, for all the CSP plants. Why when you optimize the IRR, the storage capacity decrease? Well, it depends. Because if you look into that example, the price was increased by 3 only during the 3 hours in the evening or stuff like this. So of course, if you're paid 3 times more in the evening, then the IRR shows that the best plan is that one that only captures or provides energy during those 4 hours. So it's a small storage plan. In terms of hours, not necessarily in terms of energy, actually. But if you were paid the same throughout the day, most likely the most profitable plan is not one with 4 hours, but for 10 hours or 12 hours or stuff. Does the black price curve represent a price fixed by the government? Yeah, most of the times. In this example, yes. Could you briefly re-explain the price graphic? Okay. So here we have, for the same location, which is Upington, South Africa, we have 3 different price schemes. So if you were to build a plant in Upington, what you know from the location, it's the typical weather data. So for a typical year, you know what the irradiation is every hour, what the wind direction is every hour, what the wind speed is every hour, etc. That would not vary. But the way you're paid is defined by others. Could be defined by the government in this case, the way you're going to be paid. So if you're paid in a scheme like this, which means basically, you know, during daytime from, let's say, 8 a.m. till 5 p.m., you are paid 100. No, dirham per megawatt hour, whatever. But then from 5 to, I don't know, 10 p.m., you are paid 300. And then from 10 p.m. till 8 a.m. next day, you're paid 0. So of course, you're not going to build a power plant that provides energy 24 hours, because why would you sell electricity when you're paid 0, right? So the way these price schemes are set up define in one way or another what the power plant will look like, because you're defining how the plant's going to get paid for, and of course, the optimum plant for that example ends up being something with small amount of hours of storage, because it will only sell here when you're paid so much. This is not the same as if you were paid like this, with 2 peaks, one early in the morning, one early in the afternoon. And if you're paid also in the night. Look at here, you're also paid in the evening. Lower, but you're paid. So here, an optimum would be more something with 14 hours of storage and a very large field. And here, again, it's a combination of both. At the end of the day, here, it's again, you're not paid in the evening, and you're paid the same all time, so you just want to operate in these hours. You get a, basically, if you look at this, you have like only paid during the sun, right? So this says like, add no storage, you're only paid during the sun hours. So add only enough storage so that you can operate the plant. But that depends on the way you are paid, the revenue streams and so on. Gigawatt E stands for gigawatt electric. Because we're talking about power, so it could be that it's gigawatt thermal. And we're talking about a conversion process, thermal to electric. So if I put E, it's gigawatt electric. Without any experience, how can I will be a good person with a lot of information in different fields? I wish I could answer that. How to get a self-confidence in presentation. Oh, thanks.